Well, next we take a look at Lasso, and for that we need yet another package called LARS, stands for List Angle Regression, etc. Now we are not discussing list and angle regression in general, but we'll just use it to perform Lasso. And you do need to install LARS, unlike the MASS package. So I have installed it, install.packages, LARS, etc. And then we proceed like this. I first load library LARS, and then I do not need that state data thing anymore. I'll just get rid of that. Now, LARS is the function, LARS, which will compute Lasso for us. There is no function called Lasso in our software. So I will create my matrix, which is somewhat weird. In this case, you have to create your design matrix directly. So C bind x1, x2, x3. And now you have to specify the output. So this does not take that formula interface with that little tilde. You have to explicitly create x1, x2, x3 and then keep y. So you can do that, and you can also, I have not put that that one vector, that intercept term. If you want, you can put that also. I am working with the same x1, x2, x3 as in my last example. So if I do that, I will get this. Now you'll be wondering what exactly how do I look at it. If you just try lmod, won't give you much information. It's pretty cryptic. It only says some variable 3 to 1, step 1 to 3, nothing very clear. So you will try to do coef lmod, and this will give you this thing. Now let's understand what it is doing. What it is doing is this. Remember, it is performing a constrained optimization. So you have a square over which you are trying to minimize the squared error loss, that the sum of square of the residuals. Now depending on that square, depending on that lambda, the size of the square will change. If you take lambda equal to just 0, in that case obviously your estimator will be 0, 0, 0. All the coefficients are forced to be at the origin. So the square has shrunk to just the origin. That is your first row. So when the square is very small, then it will be 0. Now you will start growing the square. After some time, x3 will enter into the picture. x1 and x2 are still zeros. You are growing the square a little bit more. Now x2 has entered into the picture. x3 is still 0. And when you grow it sufficiently largely, in that case, the square is now so very large that your least square estimator is already inside the square. So constrained optimization is same as unconstrained optimization. As a result, you are getting basically the least square estimator. You remember that minus 17, less than minus 15 and more than 5 thing, it is the bad estimator. So the last row is just your least square estimator. The first row is always 0, 0, 0. Now I said, as you are relaxing lambda, as you are growing that thing, after a stage these things happen. Naturally, you will be interested in knowing what are those stages that you might get from the lambda. So when it is 0, you know it is 0. The thing changed when lambda became this quantity. It's a pretty huge number according to their scale. I'm sorry, it is this number. So it is moving from right towards left. When it is 10 to the power minus 3, a very small number. Then you relaxed it to this extent. Now it is pretty huge. You come to this situation. After that, you make it really large, in which case your least square estimator is now part of the square, is inside the square, and then you just get this. Now you can look up further help inside the help of the LARS function. Now naturally your question will be, how do I choose this lambda? This gives you the entire picture. For that you can perform CV, and then the function is cv.lars, the same things, the design matrix followed by the response variable. The function is called cv.lars. Let's just do that. Now when you do it, as a byproduct you get a plot. The plot is informative. Here you are being shown lambda, which they call fraction of final L1 norm, because remember lambda times the L1 norm of beta. So lambda gives you the fraction, that is the fraction of final L1 norm. And here you see the cross-validated MAC. It is computing the MAC. You see, as lambda is, when lambda is 0, the MAC is pretty high. As it is increasing, the MAC is drastically coming down and then remaining pretty close to 0. Something that indicates that you must be having multicollinearity. That's why it came down drastically. And there are vertical bars around each point that gives you the standard errors. Because cross validation is based on some randomization, so you need some idea about how much variability there is. So the idea is where you first hit this elbow. From the point where it starts stabilizing, you take that value of lambda. You see that choice of lambda is not that crucial. Even if you do not take 0.2, but instead you take 0.3, MAC remains more or less the same. Things stabilize after that. So it is more or less insensitive to the choice of lambda as long as you have crossed that particular, what should I say, the particular elbow. So this is how you carry out lasso in R. Now there are of course a lot more details than I covered here. So you can, if you want, you can look up the help to learn more.